recording it too.
Yeah. All right, guys, we're going to go ahead and get started here. Hello, my name is Kenny Gorman. I am the co-founder and chief architect at ObjectRocket. ObjectRocket is a database as a service for MongoDB, Redis, and soon to be Elasticsearch. We are a Rackspace company. We are the part of the Rackspace ecosystem. And today I'm going to talk to you a little bit about performance tuning. Let me just go ahead and share my screen here so folks can see what we're talking about. And I'll kind of go back and forth between my screen and me as I talk through things. So this is a copy of the presentation I gave last night in Dallas, Texas. And we had a great discussion with folks there about performance tuning techniques. Again, like I said, my name is Kenny Gorman. I've been using Mongo for quite some time. I think at Shutterfly, one of my previous places I worked, I was, I think, the first actual enterprise implementation of MongoDB on MongoDB 1.2. So I've been doing MongoDB for a little while now, and we've learned how to do performance tuning. We've learned a lot about MongoDB over the years, and I thought I'd share some of that stuff with you. All right, let's kind of go through it. So let's talk about performance tuning here. First things first, order does matter when you're tuning databases. And so I'm going to lead you through sort of the three large buckets of tuning components that one needs to think about when tuning databases. And the thing I'm going to focus on the most here is the workload tuning, the thing that has the giant heart next to it. So I'm going to talk about schema design. That's super important. I'm going to talk about the workload tuning, and I'm going to talk about instance tuning. Both schema design and instance tuning I'm going to touch on quickly, and I'm really going to spend most of my time talking about the workload tuning. MongoDB Inc. has some great presentations on schema design. I recommend you go check those out. You can Google for those. I can post up some links later in the comments section about this too. But that's where things start. If you're not designing a great schema, then you're not going to be able to achieve number 2 and number 3 in this list. You're going to always be sort of paddling upstream. So let's talk about that a little bit. All right, so schema design. So I'm just going to give you some advice, some high-level advice here. This isn't going to be super in-depth. This isn't going to be code samples or anything like I'm going to show you in a few seconds. This is more just high-level thinking, and then you can dig in with the MongoDB docs or the MongoDB presentations to talk a little bit more about this. So my advice with schema design is, first of all, let's figure out what patterns matter. What design patterns, what query patterns are you going to use on a consistent basis in your application? And focus on the ones that you're going to be doing a lot. Right? This sounds obvious, but it's really something that's true. So just to give you an example, let's say you're building a Twitter clone, and you're going to have, say, tweets, and you're going to have users, and maybe some other collections. You might really focus on the tweet collection and its patterns. So, for example, a find of an individual tweet by ID, maybe a find of all the tweets by a user, these kinds of things. Maybe if you like a tweet or a retweet, those kind of query patterns, or if you were to ever be able to update a tweet, Those kind of things would be the things that you'd focus on. And if you're going to do those things a million times a second, or very frequently, then you're going to want to focus on those queries or those patterns the most. And that's pretty obvious advice, and it kind of goes without saying, but it's really sort of the key thing. If you're kind of organizing your thinking around, well, what things matter, and how am I going to go about doing schema design, start there. Start modeling your application with the queries and the patterns you're going to use the most, and test those patterns. Right? So don't just say, hey, in a box or in a cloud, I'm going to go out and design this application and never try it. What you really need to do is build a data set, build an example, build a test harness, and start running those queries. Learn how they work. Ensure that their response time is what you want. Test those patterns against your thesis and make sure that it's actually going to work out the way you think. And do it in a dev environment. So I'm going to talk a little bit more about development environments and production environments here in a little bit. And it's real key. It goes without saying, and it's pretty obvious for most folks, but I want to make sure that I always mention it, and that is have a dev environment. Have an environment that mirrors your production environment logically. It doesn't need to have as much data, but at least it's logically the same schema, the same queries, the same application drivers, the same application code. And make sure you're running that in your dev and test environment to ensure that, hey, this schema pattern is working the way I think it should work, and when I update a document, it's not moving, or when I try and fetch by this key, it's not really expensive. And I'm going to show you in a few seconds how to discern those different patterns. All right, so that's schema design. Let's talk a little bit about workload tuning. And also, if you have questions, you feel free to go ahead and put those in the comments box, and I'll try and get to those as we talk. I'll try not to go on further until I've answered your question, just so it has context into the slide I'm talking about. All right, so let's talk about workload tuning. Workload tuning is essentially broken down, in my mind, into two parts: the profiler and the explain. So the profiler is MongoDB's component for capturing queries or any operation into a collection and allowing you to perform analysis on it later on. Okay, so that's step one. Step two is explaining those statements and understanding what improvements they need to be made to those statements to have your database be highly performant. And it's really, and the next, let me just shift to the next slide here. It's really an iterative process, okay? So it's not something you do once and then you put away and you forget about it. As your app evolves and as your queries evolve and your statements evolve, as your various access patterns change over time, or as things get popular, you're always going to be working on performance tuning. So it's really more like an obsession and less like something you do one time. And the workflow kind of looks like this. You're always looking for bad statements. The trick here is to go out and find candidates for bad statements, and then for each one of those bad statements, go through, explain them, improve them, and then continue. So that's just a real simple way of saying, like, it's always something you're doing. You start off, it's like an onion peel. You pull off one layer, then you pull off the next, and you pull off the next, and you continue to whittle down your profiling and your queries until you get the performance to where you need it. All right, so let's talk a little bit about the profiler itself, how it works, what it does, how data gets put into it and retrieved from it. So the profiler is simply something that you turn on, like I said, as you issue statements against the database. Those statements are going to go into a capped collection, and you'll be able to analyze them later. So let's just talk about this example on the screen. The first thing I'm doing is I'm setting the profile level to level 2. Okay. Then I'm saving some data via the save statement with a name equals to Kenny. And then I'm just looking at that data out of the collection. So db.system.profile is the collection that's made in the database, in any database that you're profiling against, and that's what saves the statements. So there's two ways to turn on the profiler. One is to level 2, which I did here, and that basically records any statement. Anything that's issued against the database is going to be recorded into the system profile collection. Or you can set to level 1, comma, and then whatever millisecond threshold you want to put in for a slow query. So, for example, 1, 100. What that would mean is, hey, turn the profiler on, and anything slower than 100 milliseconds, please record it for me. Anything faster than 100 milliseconds would just be tossed away. It wouldn't be recorded. It should be noted that when you turn the profiler on, there is a slight performance hit, and it depends on whether it's 2 or 1 or whatever the level you set it to. My advice, and this is my opinion, is that you should really just think about turning the profiler on no matter what. Now, maybe you don't set it to 2, maybe you set it to 1,100 or 1,20, depends on your application. But in my opinion, it's almost always better to have your application instrumented than it is to not know what the performance is, even if the performance could be theoretically a little bit faster. So in other words, more data is better. Instrumenting your app is always better. The amount of impact or overhead that the profiler has is very small, and as long as you leave it on, it's consistently a little bit slower. So that's my advice. Turn it on, leave it on, inspect your data, and understand your data. All right, so that's kind of how you turn it on. If you want to turn it off, you can set profiling level 0. It'll turn it right off. All right, so let's kind of go through what a typical document looks like in the profiler collection. Now, this is just an overview, a high-level overview. It doesn't include everything, but it includes some of the important things that are interesting to talk about. This is an example of maybe one single document that would show up in the profiler. So first things first, it's got a timestamp at the top. That's the timestamp that the particular operation happened. The next is the operation that was performed. In this case, it was a query. And then the namespace that it was performed against. So the database and the collection that was part of that query. The next field is actually the query itself. And this is super important because this is the thing we're going to pull out of here and use to explain later. So in this case, the query was total games equal to 1,000. Okay? A couple more things that are important about this. I'm not going to go into detail about every one of these. There's a link at the bottom of the page here you can copy into your browser and just look at what all the things mean in the docs. So I'll just go through kind of the highlighted ones and kind of the ones I'm going to show you an example here in a second. So n-scanned is a very interesting attribute. What that shows you is the number of documents that were scanned to fulfill this query. And then look down at the bottom, there's one called millis, M-I-L-L-I-S. That is how long it took to do this operation. So in this case, what we did was we did a query, total games equal to 1,000. N return was 0. N scanned was 9,000,000 something something something, or 959,000 something something something, and it took 859 milliseconds. So we basically scanned a ton of documents and returned no documents, and it took 859 milliseconds. So that's kind of how you know exactly the scope of what this query was. Now, if it was insert, it would say a little bit different attributes. Update has additional elements and attributes. But this is a very, very simple example. Okay? So that's what the profiler looks like. So let me just scan forward a little bit here. I want to kind of show you a little bit about how you can find candidates to tune. Okay? So if we're going to put stuff in the profiler collection and it's going to look like this, how do we get the information out of there in order to make wise decisions about how to tune things? That's where running queries against the collection comes in. And so here's some examples of that. Now, all I'm doing here is using MongoDB's aggregation framework to pull out interesting data. Right? So one of them is response time by operation type. So in that case, I'm grouping by insert, update, delete, or query. Maybe the slowest by namespace. So I'm actually sorting by the time that it took to do something and grouping by the namespace itself. So maybe in the case of the Twitter clone, the tweets was very slow, but the users was very fast. That query would show that. Maybe the slowest by client. So if you have a batch job that's running from a particular host, and you've got maybe 10 application servers running a normal day-to-day workload for maybe an iPhone app, this would show you that that batch job's slower, or it would at least single out that query from coming from the batch host. So that would give you some insight into where to go tune that. Or last but not least, showing you where something has been moved. And I'm going to talk a little bit in a second about what a move means for an update. Okay, so these are just some queries. You can copy paste them. They're actually out on a gist on GitHub that I have linked at the end of the presentation. So if you want to actually play with these yourself, don't worry about copying them right now. You can go ahead and pull them out of the gist that I link at the end of the prezo. I would recommend that you actually play around with these. Change it to actually group by, say, in this case, by namespace. Maybe you would want to do it by the query type or whatever, and maybe you want to order by slowest or fastest. So play with it a little bit. Come up with what makes sense for your workloads. Come up with what makes sense for what you're hacking on for your projects, and maybe use these as starting points. All right. So what do I look for? So the next step is I'm going to go ahead and find these candidates, and then I'm going to explain them. Okay. And when you do explain in MongoDB, it's just a command. I'm going to skip forward here so you can see an example of it. Okay. So in this case, I'm going to do an explain on a query, right? And in this case, it's name equals 1, and it's going to show me various pieces of data about that query plan. It's going to tell me how many things it scanned. It's going to tell me how long it took. It's going to tell me if it used an index or not, etc. Okay, so this is just kind of the output. I skipped ahead to kind of show you that. Now let me go back and talk a little bit more about that. Okay, so what am I looking for when I'm doing these explains? Well, let's just kind of take it from the top here. First of all, a fast mod is the best possible outcome for anything that modifies data. So it's not for a query, but for an update. If it says fast mod, then you're done tuning. That's as fast as it's ever going to go. That means there was no document move. It was just simply like an in-place key adjustment. So for instance, if you said increment on an integer, that would be a fast mod. It would simply increment a 1 to a 2 or whatever the value was, and that's in place. It's as fast as it's going to go, and there's nothing else required to make that query tuned. So in that case, you're done. Cool. For n scanned not equal to n returned, basically what that is, and I'm going to show a good example here in a second of that, is that's basically where there's missing an index. So this is a really key and important one to look for. If n scanned is not equal or close to equal to n returned, you may have some tuning to do. Okay? And I'm going to show an example of exactly how to see that and fix it here in a few seconds. Next is key updates. So key updates are when you have a bunch of indexes on a collection, and if you were to, say, insert or update that collection, those additional keys for those indexes would have to be updated. So that tells you that your application either A, has too many indexes if you're not querying by them, or B, hey, I need all these indexes and I'm just going to have to wait. So that's an indicator that, hey, I'm updating all these keys, I've spent time doing it, you better look at these indexes and make sure you need them because, hey, it's taking time. I talked a little bit about moves, so let's talk a little bit about what that is while we're on this slide. A document move is when you do an update, and MongoDB needs to move the document out of its existing place. And the reason it would need to do that is if that document grows beyond its padding factor, MongoDB would need to reread that document and move it. So an example would be, let's say I write a document to a collection that's got my ID, and then it's got a description or, let's say, a bio field, and that bio field's initially empty. Okay, so it takes no space, it's very small, it's null. If I then update that bio and I put in 10 pages of text, then that document would likely exceed the free space threshold or the padding factor threshold of that document, of that collection, and I would need to move that document to a new space, typically the last document in line, in other words, kind of above the high water mark of where things have been written. So this is expensive because it has to, first of all, it has to reread the document, the entire document. It has to then find a place to put it, so it has to use the free list to find some space. Then it has to write it, and then it has to do all the indexes. So if there's 10 indexes on it, it has to actually perform all those operations for the indexes as well. So it's very expensive. So when you see moves in your explain plan or you see moves in your profiler data, you can be advised that those are actually going to be pretty expensive. What do you do about them? Well, in the case you have a move, like I said for my bio, you have two options. One is you pre-pad it, meaning that maybe I know that this is always going to be 1,000 characters when I update it. I could just update that to, initially I could write it with 1,000 zeros, and then later update it with whatever the text I wanted to be in there. Now that's kind of hacky, it's not perfect. Mongo 2.6 will have some adjustments for this factor, So stay tuned for the latest releases of MongoDB to help you kind of with that component. All right, and the last is lock waits. So the profiler and explain shows you how long it waited for locks, how many yields you did waiting for your query to come back, and how much time you spent waiting for locks. And I'm going to get into that a little bit later in the prezo and talk a little bit about what that is, why it matters, and kind of how you sense it or query for it. All right. So then explaining is simply taking the document from the profiler output. I talked about that query attribute. Pull that out, do an explain on it, look at those results, make corrections, and rinse and repeat. So it's pretty simple. That's the high level thing that we're doing. We're doing it over and over again. So we profile our database. We go in there. We find candidates that we think could be candidates for tuning. I showed you some queries on how to do that. Then you explain those queries. You look at the results, you try to make corrections like adding an index or removing an index or changing your document model. You test those again, and then you rinse and repeat. So it's a cycle. All right. So here's an example. Let's just go through a full example here, start to finish, and I can tell you, and you'll kind of see how this all works. So here we are. We've got the profiler turned on. We're going to do a profile.find. In this case, we're going to look for all the queries in the namespace test.testme, okay? And I'm just going to pretty print it. Okay, so I talked about what it returns. It returns a timestamp of when it happened. It shows that the query was against name equals 1, okay? Nothing was returned, okay? In this case, there's nothing equals name equals 1, which is fine. It's just an example. It scanned 32,000 documents to get that result, and it took 29 milliseconds. So it's pretty slow. Okay. Oh, I said actually n returns 1, n2 returns 0. Okay. So that looks pretty slow. So let's go ahead and explain it and see what's going on. So in this case, we're going to run that query. So here we are. We have name equals 1. So you can see that right there. I simply pulled that right from here. So you just copy paste it, right? So you're in the MongoDB shell. You just paste it out of there, copy it out of there, and paste it in right here. Call explain on it. And it runs the query, so it's not like it just tells you what the optimizer thinks is going to happen. It actually runs it, so you have to wait, and it gives you the result of what it did. Okay, so in this case, it's a basic cursor, so it's not like a find one. It's actually going to return a cursor. It returned one document. It scanned 32,000 documents. It's not scan in order, meaning that it could not act. There's no order by, so it couldn't actually use the index to order it, and there's no index anyway. It's not index only, meaning that the data was not fulfilled completely by just an index scan. It didn't yield, which means that it was probably just me testing this. There's not a lot of concurrent activity in this database. I'm going to talk about yields in a second, so we'll kind of keep that in the back of your head. And it took 14 milliseconds in this case. Now what you don't see is something in the index bounds field. Okay? It did not use an index. It basically scanned this entire collection, 32,000 documents, took 14 milliseconds, and returned nothing. All right, let's go to the next one. So what do we do about that? Well, we know we're missing an index. So let's go ahead and create an index. In this case, a descending index on 1. Okay? And then, next, we see that we did a find, just like we did before with an explain. Now go ahead and look down here now. We returned 1. Okay? We scanned 1. So instead of 32,000, we just scanned 1. And down here at the bottom, you can see that it used an index to scan to do that. So this is fantastic. Basically, this is the best possible outcome. It's basically maximum 3 IOs against the database, meaning that it scanned the root, leaf, and then date of the index, and then the data payload to actually return the document. So that's the most simple and straightforward example of using an explain plan, using an index, fixing adding the index to fix the query, and then having an improved plan. All right, I don't see any questions yet, so I think we're continue to go. Let's see, there might be a Q&A here. Stand by. All right, looks like I do have a couple of questions here. So the question is it safe to use MongoDB for a particular project that needs both scalability and performance? Since I have heard about the condition of Foursquare, which lost all of its user data, when they migrated, and then they migrated to another NoSQL database? So that's a good question. So a couple things to talk about here. Number one is, and let's just break this apart here, and I'll just talk about this before we continue on. Let's talk about performance first. So MongoDB can be a very performant database. It's not guaranteed to be. Data modeling matters in this case. I'm going to talk a little bit about data locality as we go on. And document modeling is a key component in this. So when you're designing your documents and when you're building your documents, you can design in data locality to give you great performance. It's not the only thing that gives you great performance, and MongoDB is natively fairly fast. But this is a technique, and this is a kind of a design attribute that I think, sort of my opinion, people should think about more often, and that is when you nest documents or embed documents, you're essentially instructing MongoDB to do less I/O, right? So let's just do an example here to kind of make it obvious. Let's say I have a photo sharing app, and let's say I'm querying all my photos, right? So in SQL terms, it's select star from photos where user ID equals Kenny. In a typical relational model, that might be, let's say that's 100 photos. That's going to be 100 rows and minimum 100 IOs, okay? And if that was by index, then you'd have to do the index root and the index leaf and then the payload. So it's a bunch of I/O. In MongoDB, you can actually improve upon that paradigm and that model quite a bit. If you were to nest my 100 photos in one document, and maybe it's not the whole photo, maybe it's just like a link to a file system or something, you would guarantee that's all one I/O or 3 IOs, including indexes. That is much, much more faster, obviously, doing 3 IOs than 100 IOs, and that's really where you can take advantage of performance. So, in the MongoDB world, if people are saying MongoDB is so much faster, it's so much more performant, it's because they probably understand how to model in MongoDB and build those models to take advantage of MongoDB versus using it like a relational database. So that's something I'll throw out there just to kind of start, is that performance is subjective, and it depends on how well you model and how your use case is designed, or how your application is designed to fit your use case. So that's that. In terms of scalability, MongoDB has a sharding model. At ObjectRocket, we do quite a bit of sharding. We have thousands and thousands of shards here. That is the model in which MongoDB scales. Sharding is tricky. So if you don't know what shard keys you need, you don't know the workload, the balance of the workload, and how to move things with the balancer from one shard to another, you can be in trouble. So the amount of configuration, the amount of sort of DBA talent or DBA knowledge you need, and sort of the amount of careful capacity planning, other things you need as you scale with sharding, goes up quite a bit more than if you're just using a single or simple MongoDB daemon. Now, I don't know, the condition of Foursquare exactly, or the situation of Foursquare exactly. One thing I do know that happened for their infamous outage a few years ago, or a bunch of years ago now, is that that was mostly a capacity planning issue. In other words, if you have 5 shards and you need to add a 6th, it doesn't make sense to add that 6th the minute when you need it. You need to add it a week before you need it. The reason for this is you have to move things off of the 5 shards into the new shard, and you can't do that if you don't have any room or you don't have any capacity. So failing to plan is planning to fail with sharding. And in this case, I think that's, if you go and read, if you Google for and read Elliot's comments about that outage, I think that will mirror what I said pretty closely. I think that's all I have to say about that. I don't know about data loss with Foursquare. I haven't heard that. Data loss in MongoDB, I think just to kind of address in the past there was issues with write concern. I think today with modern MongoDB, write concern is always equal to 1, and so you have a durable system. There are edge cases where, say, SATA disks have a cache on them, and flushes to disk aren't exactly getting to disk where folks think they are, but that's prevalent with any database system at that point. That's a file system nuance. So I think that's all I have to say about that one. All right. let's see. Let me just knock out a couple of these questions real quick. How do you recommend setting up a dev environment if you don't have one already? I think that's an easy one. Everybody should have a dev environment where it's on your laptop, or you can use something like Object Rocket to go provision a simple instance. So maybe it's just 5 gigs or 1 gig or very small. Just have something out there that you can use and build things against. Larger companies, folks who are used to doing this, they'll have more resources to do it. But these days with the cloud, there's no sense in not just going out and provisioning a simple instance on your favorite provider at any time. So that's what I would suggest there. All right, I think we're clean on questions, so let's keep rocking here. Okay, so we talked a little bit about the explain plan. We talked a little bit about what it looks like when you do an explain. We talked a little bit about how in this case, we were missing an index. We added the index. We explained again. Now we see a better plan, and we can move on to tuning other tuning opportunities. Last thing I want to mention here is N yields. N yields is a pretty interesting attribute. I think somewhat misunderstood and not really addressed a lot in folks' documentation. So I want to kind of talk about it here. So MongoDB utilizes the reader-writer lock. You can Google for that. That basically what that means is a yielding lock. So it's not a hard lock like maybe Oracle or Postgres or other MVCC, MVCC systems. It's a soft lock. And the way you know that it's affecting your query time is in this explain plan. So when you look at N yields and it equals some high number, you know that this query actually had to yield to other processes or other sessions while it was trying to execute. That's really key for 2 reasons. One is, if it's really high, I know that this isn't the true measure of my query. It's the measure of my query's total response time, which includes queue time, which would be waiting for yields, plus service time, which is the total time it took to do the query. I'm going to talk about this in a little bit. I'm going to break down what service time and queue time is a little bit and kind of help you make decisions on when you need to tune and when you don't. So hopefully I can give you some insight into how much that matters here in a couple seconds. And there's a couple queries you can run to figure stuff out. So that's coming up here. So that kind of leads into the slide. So that is what we call, or what sort of the old school DBAs, Oracle DBAs used to call response time analysis. So I'm going to talk about this because this isn't something a lot of folks talk about in regards to Mongo. You hear about this in kind of the relational database worlds quite a bit, but you don't always hear about it in the Mongo world. And I think a lot of these techniques, frankly, are valid and should be used against MongoDB because it helps you break down where your time is going in your queries and the overall effect of your system. So let's just talk about it a little bit. So my definition is response time, total response time, equals service time plus queue time. In other words, service time is how long it took to do something, and queue time is how long it took waiting in order for me to actually get that done. So the analogy that most people use is like when you're in a shopping center or you're at the checkout line, queue time is how long you waited in line, and service time is how long it took the folks to actually ring up your items and actually put them in a bag. Okay, so that's the typical analogy. So MongoDB exposes a couple of attributes that allow us to calculate this. It doesn't have a million different options to it, like Oracle would. It doesn't tell us how much time was spent on disk versus in index searching and other things, but it does have a couple of attributes that show the overall or high-level response time components. And this is great because we're just going to pull these out, we're going to use these in our queries, and we're just going to show us exactly what our response time was. So those attributes are millis. Millis is the total time that was taken. Time acquiring was the time taken getting a lock, okay, so that's queue time. And time locked was the time it spent locked doing the thing itself, okay? Now these aren't perfect measures, but they're close. And they'll get you the information you need to start making intelligent decisions about response time. If someone were to say, well, time acquiring isn't exactly a perfect proxy for queue time, well, you're right, and I agree. But these are the best measures we have, and they work pretty well. And so I can tell you by doing this in practice that they're pretty good proxies for these measurements. And this is really the only true measure of response time in MongoDB. So if you want to know, hey, what is the average query time that my application experiences from MongoDB, you can do it in one of two ways. You can ask your application to record it, or you can ask Mongo what it thinks. This is how you ask Mongo what it thinks. Okay? And the reason to do this is just simply to aid in prioritization of tuning opportunities. So this allows you to sort of order what things matter the most to go take a look at and start tuning. So the question I get asked the most is, okay, performance tuning, cool, I want to do it. How do I do it? How do I start? Where do I start? And so this is a query that's going to allow you to start to do that. So before I show you the code, let's just talk again about the definitions. And I won't read this out to you, but I'll just talk about it. So system profile lock stats dot time locked micros is the amount of microseconds that my session was waiting, doing something. Okay, so if I go out and I have to do a bunch of I/O, I may wait and lock for that amount of time. Time acquiring is the time I waited in order to get that lock. So if there was 1,000 sessions before me and they were all doing it, I had to wait about this amount of time to get it. And millis. Millis is the total amount of time it took. Okay? Now it doesn't include network time or things like that. So it's basically the database's opinion of how long it took. If you ran this at your application timing is going to be a little bit different because it has things like connection, teardown, and startup, network time, etc. So this is just to be clear, this is the database's opinion of how fast something or how long something took to run. All right, so this is just a simple query that tells you, actually it's not so simple, it's an aggregation query. It's got a bunch of parts to it, but this is what tells you what your response time is on the database. This, just for reference, is linked in the gist or the GitHub that I have linked at the end of the presentation. So don't try and like copy it down now or anything like that. Don't worry that you need to copy it down now if you want to try and run it against your database. Just feel confident that I'll show the link at the end of the pre-zone. All right, so let's just talk a little bit through this. What are we doing here? So if you didn't already know, the aggregation framework is MongoDB's component that allows you to basically run aggregations. So in SQL speak, that's things like group bys. So we can do groups, we can do sums, we can do counts. And it's cool because it's a pipeline operation. The design is basically a pipeline design. So the first thing I can do is pipe through this project pipeline. Okay, that's the first component. The next one would be through another pipeline. And lastly, the group pipeline. So what I'm basically doing is, in the first pipeline, I'm dividing to make milliseconds or microseconds into milliseconds. The next, I'm actually doing some math, and lastly, I'm doing a group by. Okay, so there's a lot of text there, but it's pretty simple. It's just 3 steps, and I'm using those 3 components that I talked about before, and so that gives us this kind of output. So let's just kind of go through it. The first one is an insert. Okay, and so it's grouped by operation type. So you'll get 1 document per operation type. In this case, just insert, just update. But if you had queries, there'd be 1 for query, there'd be 1 for command, there'd be 1 for delete, etc. But let's just talk about insert and update because they're the most interesting here. So the average response time, the first line here, is how long, on average, things took to complete. Okay, so it seems pretty fast. It's less than a millisecond. The time it took acquiring is pretty fast, but the time to acquire a lock to do a write is pretty slow. Okay, we spend a lot of time waiting there relative to the other operations in this document. And then the lock time was pretty quick. So okay, we did a little bit of lock time, but man, we waited quite a bit. Okay. What that means, what that most likely means, is that we're waiting for other sessions to complete. So this might have been during a very, very high insert time, and this particular operation had to wait in line in queue time to get the lock in order to do its work. And then when it got the lock, okay, it wasn't super fast, but it completed relatively fast. So in this case, what you might do is you might say, I'm starting to see response time go down because I have a concurrency problem. Okay, so if you did this on your dev system with just 1 session, you'd never see this stuff. So that's why it's important to run this on your production system, actually look at your actual workload and see that this is actually affecting you. This is kind of the only way you can see this stuff, so this is why it's super important. All right, So that's that. So in this case, I might work on concurrency. Like let's say, I'm just making up a use case here. I had 1,000 app servers, and 1,000 app servers are all inserting, new sign-up requests all at once. Another solution might be, hey, I'm going to actually use a queuing system. Maybe I'm going to use RabbitMQ. And I'm going to queue all those things in that queuing system, and then I'm going to dequeue them from a single worker. That single worker would have a concurrency equal to 1. And so I would not actually have a lot of locks on the database. The lock rate would be fairly low. Another thing you can sanity check this against would be like MongoStat. If you looked at MongoStat, you should see a fairly high lock percent. By that I mean, not a double digit or above. And you might see the time to write the QW column have some entries in it. So just kind of gluing that all together for you. All right, let's talk about update a little bit. So in this case, the average response time is a lot slower than it is for the inserts. And the time to acquire the write is huge relative to the other components here. And when we do it, it's fairly slow to actually perform that operation. So in this case, I would say, hey, look, we do have a concurrent situation just like we had before. Things are taking a long time to get completed. But it's also because the time doing it is pretty slow. And so in this case, you might say, why are my updates so slow? Maybe I'm doing bulk updates. Maybe I'm doing them highly concurrently. Maybe I'm doing moves. So that would be something. What I would do in this case is I would actually go back in the profiler. I'd look at all my updates. I'd order by milliseconds, and I'd start to pick out those bad queries, the slowest ones, and start to look for tuning opportunities there. Okay, so that's kind of like the full life cycle. Now, the real killer thing here is once you've gone to the level of, like in this last slide, of actually pulling this data out, now the next sort of holy grail is to actually graph that over time. Because any one moment in time is interesting, but not wildly interesting. What's wildly interesting is when you run this over time, and you can see it throughout the day. You can see your peaks, you can see your valleys, you can see your response time during your peak hours, maybe during weekends or nights, and you start to understand what's normal performance for your system. So that's what response time is all about. If you know that your response time for your system is always less than 50 milliseconds on average, when you see something at 200 milliseconds, you know something's wrong. That's a tuning opportunity. What happened there? Let's go figure out and fix it. Maybe it affects your customers, maybe it doesn't, but at least you know something you didn't know before, and that is, hey, on Thursday nights we have this peak, the system goes down to doing 250 millisecond response time. On Thursdays, whatever's happening, we need to go tune that. And maybe you start to look, like I said before, you start to run the query that shows the different clients and starts to look for batch jobs, because maybe Thursdays, when you run the batch job, something like this. Or maybe the first of the month or the end of the month, things like that. If you know that the database is slowing down, you know that you're affecting your customers. And you know that the response time of your iPhone app or your analytics app or whatever else is affected. And you can make those judgment calls. There's really no other way that you could understand the overall performance characteristics of your database if you don't use some sort of tool like this. In this case, basically, I just wrote a little bit of Python here. You can go check out my GitHub repo for that code snippet. It's just a starter. It's nothing complicated. It's nothing awesome. I'm sure you can improve upon it greatly, and I'd love pull requests if you want to play with it and improve it. In this case, it goes into MongoDB. It pulls out this response time data and it shoves it into Graphite. And so here's a very simple example of that Graphite graph. You can see some peaks there. Those would be tuning opportunities. Okay, so just to kind of pull one out, between 1836 and 1838, I had a huge spike in my inserts. Okay, what was that? Maybe that was a DQ of a queuing process, or maybe I had like a new sign up, and whenever a customer signs up, they immediately do 7 tweets. And okay, got it. That's a normal pattern, and I can account for that. Maybe I need to go and tune the tweet insertion mechanism or the insertion. Maybe that tweet collection has lots of indexes, and I could look for opportunities there. So that kind of gets your thinking down the road of like where to tune, what's important, and when it matters to your customers. All right, so that's kind of your workload tuning in a nutshell. I know that's a lot of stuff there, and I know I kind of went over kind of the basics there. Typically, I try and talk about just the very core components. Try and lead you through a few examples. one of the most important things you can do is read the docs about the profiler and about explain plan. I have those links at the end of the prezo. That's going to get you up to speed with every attribute, what it means, and why I tune it. So that's kind of like a homework or a follow-on if you're really interested in this stuff. Okay. Last but not least, this is sort of the end of the setup here. I want to talk about instance tuning. Now, instance tuning is only really useful if you've really considered both your schema design and then your workload tuning. If you're tuning, your file system read ahead, but you haven't tuned your documents, you haven't tuned your document design, or you haven't tuned your workload, you're really kind of wasting your time, because once you do tune those things, things are going to change on the host system itself. Maybe you need different read aheads, or maybe you need different cache sizes. Maybe your hot set's completely different. So, that's why order matters, and that's why I said that in the very first slide. All right. So first and foremost, the most important tool I can say in anything having to do with performance for MongoDB is MongoStat. MongoStat is a great tool. It's in the binary directory, the bin directory of your distribution. When you run it, it gives you output of various components about MongoDB on a per second basis. It tells you things like the number of operations you've been doing. It tells you about the amount of cache misses you've been doing. It tells you about things that are queuing and things that are locked. So it's a really great tool to have running. I recommend it highly, and kind of learn about that. Google about it a little bit. Look it up on the docs, and arm yourself with understanding of MongoStat. It's a key tool. Cache management is a big deal. That needs to be addressed if you're thinking about total performance. MongoDB works using memory map files. It does not use shared memory segments or anything in the itself. So it utilizes the OS's caching mechanism to cache buffers. And understanding what buffers are in that memory matter quite a bit. There's some tools in 2.6 to help you identify the hot set. And identify like what your workload looks like at normal runtime. Just some tips here. This is kind of high-level advice. I'd say, you need to know what your system looks like under real production workloads. So, that basically means running MongoStat against your production database. You can see the defaults column in MongoStat, and that'll tell you the number of misses from your cache and what then is affecting the disk. And you can also look at the disk. I mean, you should see. IOStat would be a tool that you use to show you, the I/O utilization of those disks, and work through that. Like, it matters. So when you're thinking about modeling, the more data that you can kind of keep compact, the more data you can fit in cache. That's pretty obvious. So if you're using, say, instead of making giant documents or even giant keys, right? Like so, a key could be the date I entered this document, or it could be, D for date. We're dealing with millions and millions of documents. Key size matters. That makes a more compressed document. The kind of data structure you're using matters, because that keeps a more compact document. And the way you nest things, or the way that you nest attributes within a document matter too. So, going back to that photo example, if you were going to select 8 documents for 8 photos, that would not be a very compressed model. If you were to select one document with a nested array of photos, that would be more compressed. Okay, so that's kind of a dimension that you should be thinking about. Other than kind of saying, think about compression, understand your hot set. Those are very obviously broad topics and high-level things, but they need to be considered when you're thinking about total performance tuning. So locks and sharding are an important component as well. MongoDB has a database-wide lock. Most people probably know that. They've probably heard the term MongoDB and locking in the same sentence before. But it should be noted that MongoDB's locks are a little bit different than other databases. So when you hear that, don't immediately just, oh my God, it's a whole database lock. The database is locked, one at a time. Yes and no. It's a yielding lock. So I showed you the yields earlier in the explain plan. That's how you know exactly what's yielding, and you know how many locks that you're basically being taken. So if you're running MongoStat and you see lock percent at 5%, that might be okay on your system. Maybe 50% is okay on your system. I can tell you if it's 80% or close to 100%, you're going to have a pretty slow database, or maybe a database you consider down, it's so slow. So it's something to consider. The way that you design around locks or get more locks, at least in Mongo 2.4 and 2.6, is to add more databases or add more collections in different databases, I should say. So using the example of tweets, maybe my users collection is in database A, and my tweets are in database B. Okay, that would give me a lock scope per user tweet and per user itself. So that would give me 2 scopes versus 1, and simply saving them in a different database would give me that advantage. So that's that's a pro tip or whatever. The other dimension in which you can get more lock scopes is sharding. So if you decide to shard your tweets by user ID, then you could do both. You could actually get 2 databases, one for users, one for tweets, and then you could get, say, 4 shards. So that would be 8 total lock scopes. You'd have a much more granular system than you would if you just had that all in one database. So that's some things to think about. And frankly, some folks may shard just to get lock scopes. If your database is doing that many updates and there's nothing else you can do, you can't tune anymore, then you may need to shard just to get more lock scopes. It's a valid reason for sharding. And last but not least, hardware. The cloud is sort of abstracted hardware out these days, but one thing that is prevalent is SSDs, and I can say with quite a bit of experience that MongoDB just works great on SSD. The cache management question becomes a lot less important when your disk I/O is much faster. You can do clever things like you can symlink your oplog over to SSD and make that faster. There's quite a bit you can do with SSD, and with the prices kind of rocketing towards zero on hardware, it's fantastic to as a database DBA or database engineer, DevOps guy, to be able to go out and say, yeah, I'm going to use all SSD for this stuff. So I highly recommend, and you should test this. You should use your dev environment. Go get an SSD dev environment. Go get a spinning disk dev environment. Test the two against each other with your workloads. Compare and contrast the performance of those things. Maybe for your work it doesn't matter so much, but my experience is that it makes a great deal of difference, especially bang for the buck in terms of pricing these days. So that's just kind of a direction I would steer you in. It's not any sort of hard requirement. All right, so these are some of the links I told you that I would have. We'll be sure to follow up and make sure that these links are available after the presentation, so that you can click on them and go to these things. Let me just kind of go through them so you kind of know where to go from here. The first link is the first link here. Let's see if I can highlight these. Nope, I can only highlight them all. Let's see. So the first link here my cursor is on is basically some helpful queries that I put on my blog that you guys can check out, copy and paste them into your projects, play with them, hack on them, change them up to kind of meet your needs. I just thought, some of these things just get you started and get you kind of thinking about running things against the profiler. The gist here on GitHub is a list of all the queries that I talked about in this prezo. There's kind of enumerated every one of them, so that's a great place to go. Fork it, contribute, just copy paste and do whatever you need to do. Hopefully, this isn't an exhaustive list, but it's some of the handy ones that I found. And hopefully it'll get you started in your projects and kind of get you used to and thinking about querying the profiler. And look, it's fun. So these queries get you started, and you can kind of play around with it. The next one is the utility that I use to pull out data and put it into Graphite. That's pretty cool. It shows you response time over time. It's not exhaustive. It's not it's a helper just to kind of get you started and thinking about how to do it. But anyway, check that out. Next is a sample data set. If you don't have data, a data set that you're using currently, or you don't have anywhere to start, like let's say maybe you're considering MongoDB and you're not really convinced of it yet, or you haven't really started on your project, or you don't have a lot of data, you can go check out this Ocean data repository. You can pull down a dump, import it into your database, and play with that. So you can run these, run things against that, profile them, and kind of play with it. And the last 2 links are just simply the Mongo docs, the database profiler and the explain plan docs. Both of those are great follow-ups for how to read about the profiler and explaining, and how you can go ahead and take your projects further with those things. I didn't go over every use case here. I just went over the simple one, but you were missing an index. But there's a bunch more stuff to learn by going to those docs. All right, so that's pretty much it. Let me go and see if we have any more questions here. All right, let's see here. This query is, my queries are simply field value with an index on field. The collection has 1 billion records, of which I'm retrieving 50 million. Still continuing, let's see here. Seems like there are alternating spikes of Mongo CPU, 100% 2 cores, and times when it appears that MongoDB is waiting on I/O. What kind of things can I try to improve query time? Okay, got it. Let's see. Field value with an index on field. The collection has 1 billion records, which I'm retrieving 50 million. Okay, so here's the thing. You're asking for 50 million records. No matter which way you slice it, you've got to return 50 million records, if I'm reading this right. And also, you're using the term records, which means you're probably a database person, not necessarily a MongoDB person. If you're reading 50 million documents, then you're going to have to wait for those 50 million documents to be returned from MongoDB. So even if it's an index lookup, right? So each one of those fetches is going to have to go to the root, to the leaf, and to the payload of 50 million times. And it's going to have to return that data. And maybe that data is in cache, or maybe that data is in disk. If you see CPU spike, I'm not sure about that. MongoDB is pretty easy on CPU. But if it's waiting on I/O, yeah, that makes tons of sense. That just means it's a miss in cache. It's got to go to disk. The way to fix that is simply to bolster your I/O. So I talked about SSDs. I talked about, you can obviously increase your cache, which is memory. That's generally more expensive than increasing your disk. It depends on the response time you're looking for. 50 million records. It depends on how large each one of those is, as to whether or not you could do that with make it in memory only or whatever. So there's a few options there, but the bottom line is you're doing an index range scan, right? So you're returning many values by index, most likely here. You're returning a significant number of documents, and you're going to essentially have to wait for that I/O to continue. By the way, one thing to note about that is that's a fairly locky operation. Each one of those fetches, 50 million, requires a lock and would require some other session likely to yield. So that's something to think about in a system where you're returning huge amounts of documents like that. The other folks on that system who are concurrently accessing the database are going to experience waits. Another or a technique to work around that would be to, hey, can I move this data off of this system to like a reporting system and actually retrieve it from there? Or maybe I use some other technology, like maybe it's a Hadoop, like a MapReduce kind of thing. So there's a few other tools that you might want to think about. You might want to think about splitting it out. You might want to bolster your I/O, or you might try and be more selective. I don't know if it's 50 million documents, it may be a reporting kind of thing, and you might try and read that off a slave, okay, and not off the primary, and that might give you a little bit better performance because it wouldn't have to wait for the lock. All right, I think that's that. Next question is, what options do I have for tuning MongoDB? Oh, okay, that's the first part. Someone was telling me that's the first part, so I think we solved that. I think that's pretty good here. I think I've answered most of these questions here. Alrighty, so just to wrap up here, kind of give you a heads up here. If you have any questions on any of the stuff that I talked about, you can go ahead and ping me via email. It's kgorman@objectrocket or kenny@objectrocket.com, or hit me on Twitter @KennyGorman. I'm more than happy to talk about this stuff. This is a very kind of quick and informal way to kind of talk about performance tuning. Again, I went through some of the most simple examples, so I didn't get too complicated and confuse folks. And so go try those queries, go hit those links, play with them, learn a little bit. And if you're confused or want more info, feel free to hit me up or hit the docs. And would love to talk more and more about performance tuning. It's not, again, like I said, it's not something you do on a Thursday and then you never do it again. It's something you do every Thursday. And it's something that you do kind of religiously. to make your system fast, and especially before rollouts, especially when the code has changed or the application's changed, or maybe you've been featured in the App Store, or you have a big promotion, or things that change your application's profile. Those are the best times to go back, revisit your workload in development environment or in production environment even, and figure out those opportunities for tuning, and then go attack them with the profiler and with Explain. All right, guys, thank you so much for joining, and we'll see you next time. This is a weekly series or a semi-weekly series, so we'll be back again to talk more about this stuff. If you guys want to talk in more detail about a particular topic, throw it in the comments, and we'll drill down on one of those topics in a subsequent hangout. So anyway, thanks for coming, guys, and we appreciate it.